Okay, everyone. Welcome to session 11 of this NPTEL course. We are going to focus on deep learning today. And first is CNN. And first, you're going to go through some of the theory, and then we can set our eyes on the problems. So, to get started, so you'll understand first what is deep learning, and so to get started, so we have a image classification problem. Oh, shit. Okay, so we're continuing. So deep learning, the first is classification problem of an image. Uh, so this is, as you can see, car. So there are several layers of feed forward networks. Okay, and so there is a traditional way of doing it, the computer vision way, in which we are identifying the corner features with shift or HOG, and then we are using some unsupervised means like k-means classifier, and some supervised means like SVM to classify that is as a car. Okay, but the deep learning approach is that we are using feature the feature extraction and classification happens simultaneously in the neural networks layer, and so that is how it is done. And so next what we are doing is that the input image that are given, so first it is able to learn lower level features, and then after that it is able to learn higher level features at the subsequent layers. Okay, and eventually it is learned whether it is a which object is it. Okay, uh, so this is how it is done. Okay, so deep learning, as it is having lot of hidden layers, it requires larger data for accuracy because a lot of parameters are there which need to be learned. It also gives higher accuracy and longer to train. So to speed up the process, we use GPUs, okay, graphical processor unit, which use simultaneous processing to speed up the process. Uh, so so um, so continuing. Uh, so as you can see with the traditional ML algorithm, if you increase the size of the data, there is no significant change on the performance of the uh, algorithm. While when it comes to deep learning algorithms, there is quite a significant change when the size of data increases. So this is the traditional approach that is being represented, and next what we have is this supervised learning. Okay, uh, so this is the with SVM and random forest. Okay, uh, so these are very tedious and costly to develop such handcrafted features. Okay, and these features depend changes case by case, and so as you can see throughout the training process, what happens is that first low level features are learned, and then at subsequent levels layers high level features are learned. So we use ReLU usually at the hidden layers due to the vanishing gradient problem, which does not happen with ReLU. Okay, and next is that when we are using fully connected neural networks, what happens that the number of parameters very quickly blows up. As you can see, a quite smaller image, 400 cross 400 cross 3, has approximately 230 billion parameters, and so that is what you can see. Next, next what we have here is that uh, so so first we are doing understanding what is convolution. So here we pass a filter. So this filter is the radial basis filter. Okay, so it gives out the uh, high intensity features. Okay, this is the borders of the objects here, and that is how we calculate. So this is the importance of the convolutional layer. Okay, so this filter provides this convoluted image, okay, or feature map as we call it. And next what we have here is so with convolutional layers, as you can see, the number of trainable weights reduces dramatically. As you can see, there are four parameters in this filter. So if it is applied 100 times, then you will have 400 features, not more than that. Okay, but in the ANN you had several features, right? So that problem is not there. Okay, in ANN the number of weights dependent on the size of the image, but here the number of weights depend on the size of the filter. Okay, so it reduces the weights number of weights considerably. So we're just showing how the convolution is done. Okay, and so using this convolutional layer, as you can see, we can get a feature map like this. Okay, uh, okay, So if it is a colorful image, we have to do convolution thrice for RGB. And next, what we have here is, so so what does pooling do here? Pooling is another operation similar to convolutions. So in pooling, we are taking, if in the case of max pooling, we're taking the maximum element in that filter, and in average we're taking the average of that. Okay. And next, the summary page is very important. As you can see, we are applying the convolution, so you're getting the feature map. The output size of the feature map, width or height, is given as this. So you see here, we are applying convolution and max pooling repeatedly to create this convolutional neural network. So here first we are applying a filter 64 times, the next again for 64 times, and after that we are using max pool. Okay, so it has reduced the size of the image, as you can see. The stride is some uh, some number greater than 1. Okay. So as you can see, this filter, when applied repeatedly, it produces this feature map. And so it is only connected to 9 input pixel of the image, not to all the pixels. So so the number of weights has considerably reduced. Okay, and similarly like that. Okay, so in this case, what we're having is some shared weights. Okay, shared weights results in even lesser number of weights. As you can see, both the weights are same to calculate this convolution. So these are the type of activation functions that can be used: the step function, the signum function, linear function, ReLU function, sigmoid function, hyperbolic tan. So in this classification problem, after the convolution pooling combination, we are using a fully connected layer to classify and get the softmax probabilities, which is the probability of it happening. Okay, the highest one gives the probability. this is the first little understanding into the convolution that we have done. Okay, and next we go to some problems here. Sorry, the slide wasn't presented. Okay, so let's continue solving the problems here. So the first question is, what is the receptive field? So so let's check out this problem. Okay, uh, so receptive field is the filter that we're using. The area that it covers is the receptive field. Okay, so let's check out the option. It is the name given to the connectivity of neurons only to a local region of the output volume. It is not of the output volume but of the input volume. Okay, so option is D. Okay, okay, continuing next, what we have here is that why is preferred to keep the kernel size small. So we have this problem. So, so the question is that why do we need to keep the kernel size small? Uh, and the answer of that is that uh, so so if the kernel size is kept bigger, so you must understand what happens is that it is getting closer and closer to the fully connected network that we have, because it is connected to each and every the the new there are each and every is the connections has been made to each and every pixel of the network. Okay, so that so if the kernel size increases, it approaches a fully connected network. Okay, so it is important to keep the uh, kernel size small so that the parameters does not increase with kernel size. Okay, so the answer is this one, grows quadratically with kernel size. Got it. Next we have this problem. So so we have this problem. So the image size is image can be image, or it any can be any feature size. So that is 63 into 63 into 16, and so so these are the this is the size of the image 63. Actually, it cannot be an image. Okay, so it is a feature space. Okay, uh, okay, so we are using 32 filters. What it results in this depth of 32. That is simple enough. Okay, the number of filters there are, that is an depth. Okay. Next, the output size that we have is W minus F plus 2P by S plus 1. Okay. Okay, so that is it. So there is no padding, so P equals to 0 here. Okay. And what we have is W minus F by S plus 1. So the what is the stride here? Stride is 2 here. The width of the in feature space is 63, and F is the size of the filter, that is 7. So this becomes 56 by 2 to 28. Both sides will 28. Plus 1 is there, so that becomes 29. Okay, so this is the answer. Okay. So which activation function is less prone to vanishing gradient problem? So it is ReLU, because the gradient of the ReLU is a constant. Okay, and but leaky ReLU is there. Okay, so leaky ReLU is a better option because below 0 it will the ReLU becomes 0. Okay, but leaky ReLU does not become 0. So leaky ReLU is the best example here. So answer is leaky ReLU. So for the rest of this problem, what we need to do is to go over the papers that are uh, corresponding to this networks. Okay, which have given the structure of the network. Okay, so first what you're going to do is look at VGGNet, because the next question is on VGGNet. Oh. So it asks that in VGGNet, what is the size of the kernel and the stride? Okay, so we have to find this information from the paper. So let's figure that out. Okay. So the representation, as you can see, it is convolution the receptive field size, so that is 3 cos 3. Okay, so that means the filter size here is 3 cross 3, so this is the option. Okay, so answer is this one. We'll also look over the what is the stride here. So the stride is should be 1. Okay, so let's check that one. So let's check that. So the number of channels. So the size should reduce, right? For it to be stride greater than 1, right? But let's see where is the thing. So 224 cross 224 is the size, okay. And okay, but how can you find the size of the uh, image consequently through every uh, convolution? So let's try to find that. Okay, so let's read this one. So let S be the smallest size of the isometrically scaled training image from which cropped, while the crop size is fixed. In principle, you can take now acha, completely spanning the smallest side of the training image. So size of the feature map is fixed. That is what I think. Okay, there's no mention as such. So the answer is this one, right? And the next, what we're having is, so what is the primary function of the inception module in googlenet? So first we need to find the googlenet paper. So this is the googlenet paper that we have here. So this is what you need to find. That is the inception module. So in this googlenet paper, we need to find this inception architecture. Okay. So uh, uh, so as you see, so the main idea of the inception architecture here is to find a locally optimal sparse structure, okay, in which this convolution vision network can be approximated and covered by readily available dense components. Okay, so that is the overall idea. Okay, and so if you look at our question, what is it? Uh, so uh, So it really asks about the structure of the inception module. Okay, so maybe there is a picture here. Okay, yes, there is. Okay, uh, so focusing on that. So focusing on that, let's look at the structure here. So so this is the previous layer. So this is a naive version. Okay, means like the rudimentary version. Okay, uh, so there is 1 cross 1 convolution, 3 cross 3 convolution, 5 cross 5 convolution, 3 cross 3 max pooling. Okay, and then we apply the and then filter. Okay, so this is applied parallelly here. And next, in this problem what we have here is this previous layer and this 1 cross 1 convolution leading to filter filter concatenation. um, so we have to see what is filter concatenation here. uh, there hasn't been written. I think there's something, but like I have not much idea about it, but the question can be solved with this diagram only. mm, So, so the third option matches the best. As you can see, it incorporates parallel convolution operation of different kernel sizes. Okay, so these are convolution operations are parallelized, as you can see. Uh, what is the importance of that? I don't know for now. Okay, but I can check out. But this is the structure of the inception module, as you can see. So it parallelizes the convolutional operations. Okay, so that should be the answer. So next question here is uh, question 7. So how do we control exploding gradient? So not a tough one actually. So we do it by gradient clipping. So gradient clipping is nothing extraordinary. What we do is we keep a upper threshold, say alpha. Okay, and so what we do is that if the gradient, suppose what we represent the gradient del by something del w, can be any parameter, right? Ij, whatever be the layer and that node. Okay, so this value should be less than or equal to alpha. So this is some value, a large value usually, but not infinity, because it can blow up to infinity, leading to meaningless answers. Okay, so we have restricted this to alpha. Okay, and this is called gradient clipping. Okay, next next is this next we're understanding like what is the importance of stride here, what does stride do. Okay, uh, so again, not a very hard problem. So stride, as you see, means like we are jumping. What is the by what amount are we jumping from uh, one set of pixel values to another? Okay. So what happens if your stride is 2? The size of the feature map reduces by half. What I mean is like you divide the size of the feature map with half. Okay, by 2. Okay. Uh, so so means at every step you're skipping one layer. Okay, one width, as you can see. Okay, so you do that. Okay, so it is applied n times, right? N is the depth, so it is, if you're skipping one every time, so it leads to reduce reduced by half, right? So that is the special dimension reduces by half. Means okay. Okay, so this is the answer. Okay, so question number 8 is this. And next question: how many convolutional layers are in AlexNet? Okay, for that we need to go to the AlexNet architecture. And so so AlexNet is one of the most important paper actually, uh, because it introduced the concept of ResNet. Okay, so let's go over these actually in detail, which can help you a lot. Okay. uh, this is the definition of the architecture here. Means they have defined it here. So this is the architecture of the CNN model. So there are eight layers with weight. The first five are convolutional and remaining three are fully connected. Okay, so we got our answer. The number of convolution layers is 5. Okay, that is easy enough. And next, what you are going here is, you must study it carefully, because it is one of the most important paper. It's like breakthrough paper. Okay, so there are three fully connected layers here. Okay, output of the last fully connected layer is 1000 with softmax. So there's 1000 classes, which it implies. So it produces a distribution of 1000 class labels. So there's multinomial. So it maximizes the multinomial logistic regression objective. Okay, and the kernels of the second, fourth, and fifth layer are connected only to those kernel maps in the previous layer which reside in the same GPU. Okay, so what they've done is actually they have divided the process into two GPUs. For that, what they're doing is they have divided the feature half. Okay, so in two parts. Okay, so they can separately train on two GPUs. Okay, and so what we have here is that okay, and okay, so every convolution follows a max. Means every max pooling follows a convolution layer. Okay, here, uh, and this is how they have done. So first they're using a feature size, means like kernel size of 11 cross 11, and they have used it 48 times. Okay, um, yeah, and so that is the result that we are getting. Okay, then max pooling. Okay, and with the size of the image is 27. So size is reduced by half, as you can see. So what it means is that they have used a stride of 2 here. Okay, so that is it. And right, next, so here the stride is 4 in the convolution. So that is, you can see the size of the final map has reduced, has become 1/4, okay, it become half, okay, and like that it continues, okay. Max pooling again half, okay, so the size has become 13 now, and 13 cross 13, and I think this operation is convolution with stride 1. The size has not reduced, and another max pooling, but without any stride here, and then the finally dense layers, and so this is structure of the network, okay, and so I'm sorry, here the skip connection is not introduced, okay, I mixed it up, sorry, I think it was introduced somewhat later. For actually deeper networks, you need to have skip connections, because without that, the accuracy, the training accuracy, even the training accuracy falls. Okay. Uh, so that is the problem here. Okay. And so they have also used dropout here, and so dropout is another theory, means you drop that neuron with probability 0.5, which results in a network which is more robust, okay, and it does not learn, it does not overfit the features, okay, resulting in better, so it results in um, better classification. So we're covering the Alexnet paper here, um, and so I was explaining the architecture, and then they are using dropouts as well. Dropouts is an important concept which we have not covered here. uh, so as you can see, the total accuracy we have got from the classical method of shift plus a full this then feature selection and then classification. So accuracy is quite low, okay, in the data set, but with the AlexNet, the accuracy has been quite significantly above the classical way of doing it, okay. So this is an important actually picture, so it shows what is the highest probability of being it a mite, okay. So it is collected classified as a mite because it provides the highest probability to mite, okay. Container ship as well the highest probability, motor scooter highest probability, leopards it's doing it well, okay. So here it has gone wrong, okay. So this is a grill car, not a convertible, okay. So that is quite challenging though, like we have no knowledge about what is a grill car, right? But so that's quite challenging as well, okay. So there are different type of mushrooms here, okay. He had again done the mistake, and so this is you can see, okay. Not always does it classify correctly, but the problems are also very challenging, not easy. And next what you have here is mm, so this is the AlexNet paper, okay. After that, this to improve accuracy they use skip connection, okay, ResNet connections, okay, and without ResNet this dropouts and batch normalization. Even in ResNet batch normalization important, but if you are not using ResNet, then uh, using of dropouts is very important. Uh, so that is what they have explained as well. That without using dropout, they are overfitting the data set, training data set, but performing poorly on the test data set. Okay. So there is a paper on dropout as well. Okay, and batch normalization. So you should check out those as well. So this is the dropout paper. So the lead author was a Indian from IIT Kanpur. Okay. So this is the paper on dropouts. So you're dropping out the one means randomly one of the nodes. Okay, and so it results in node the node not being uh, what do you call that, specializing in classifying some features. Okay, so what happens at that if it is dropped and it specializes, then it cannot do it, right? It cannot classify using that node. Okay, so it cannot over specialize. Okay, and so what happens that every node has to learn some of the way of classifying some of the features in the feature map. Okay, so 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 what happens is that with that you have a more robust network. Okay, so that is the importance of dropout. Without that, what happens, and it leads to overfitting. Okay, in this deeper networks. Okay, so you can read this paper, and so this is the mass behind that. Okay, and so significant performance improvement in every type of data set here. MNIST, CIFAR 10, CIFAR 100, ImageNet. Okay, that Alexnet was on ImageNet data, so it was well performer of the ImageNet data challenge. Okay, that was there. Okay, so as you can see the plots as well. Okay, and these were the important things. Okay, and so this is it really. So this is a batch normalization paper as well. Okay, and the next significant most paper is the ResNet paper. Okay, which introduces why this skip connection is very important. Okay, so let's see that paper as well. uh, so so it is this you can see. uh, so we have a 20 layer network and 56 layer network. What is happening is that with layer increase, the training accuracy should improve, right? But that is not at all the case. Okay, training as well as the testing has fallen. Okay, here they plotted training error. Okay, so that is why it is at a higher level. Okay, so with more number of layers, the performance does not improve. Okay, so that is the concept that they have here. Okay, the explanation is here. Okay, this is the residual block. Okay, so they are mapping first to a without the skip connection. Okay, so what they're doing is they're mapping x to fx plus x. Okay, with the skip connection they are mapping to 0. Okay, so so okay, this is shortcut connection or something. Okay, and so so this is reference to 0. Okay, so it is easier to optimize the residual mapping than the unreferenced mapping. Okay, that is the concept they have introduced here, and for that the skip connection is important. Okay, and more explanation here as you can see. So you can make deeper models. Okay, with this concept. Okay, which would not have been possible without the skip connection. I think the limit is 8 layers, 8 convolutional layers you can use at max. At max for without resonate and it performing well. Okay, if more layers are required to improve the accuracy, then you need to have resonate connections. Okay, so that is the importance of resonate, very important paper. Okay, and so that is the importance of resonate here. Okay, so that is the resonate we have here, and So the next question is that which of this network has the highest number of training parameters, maximum number of training parameters? So very easy question actually. Actually, you actually don't even need to count or see the paper actually. As you could see in the VGG16 paper, the number of fully connected layer was 3. Okay, in none of these other papers that they have used so many type number of fully connected layers. The number of fully connected layers actually blows up the number of parameters and that this model have. Okay, so that is why VG16 has the highest number of parameter, maximum number of parameter to train on. Okay, so this is it. Yes, so we're done with most of the things. Okay, in convolution the ResNet, what happens is that you can add layer upon layer leading to very large networks. Okay, with extraordinary performance. So ResNet 101, so what does it mean? You have 101 layers of ResNet, skip connected ResNets. Okay, so there's 50 layers of ResNet. Actually, these are already implemented, and you can get these models easily. Okay, the backbone of the model. Okay, you don't need to write the model again and again. So this is the idea. Okay, and the paper is by Microsoft Research from Japan, I think, and one of the most important paper in convolutional classification segmentation work. Okay, so so this is it really. Uh, Not much to do other than this. Um, okay. Any doubts? Any doubts? Binayak?
Yes, sir. Sir, sorry, sir, I joined late. So can you please so the assignment questions again, sir, so that.
Okay, okay, okay. I can help you with that. So, so first we found out what is the receptive field. So receptive field is actually size of the filter. Okay. So if the filter size increases, what happens is that from this presentation you can see here, professor's presentation only. Uh, so so yeah, the as you can see this filter. Okay, so what happens is that this filter value that is after the convolution we're getting 3 is connected to uh, 9, right? 9 pixels here. Okay, 9 pixels. Okay, this is it, right? So if the pixels if the filter size increases, okay, so what will happen is that it will connect it to more and more number of pixels. Okay, if the number of the size of the filter becomes equal to size of the image, what will happen is that it's connected to all the pixels, which is the fully connected situation. Okay, so you don't want a fully connected situation, right? Okay, okay, there is another question here, but like so this receptive field, so it is the uh, connectivity of the neurons to local region of the input volume. So the local region is this filter size. Okay, and it is connected out to the input volume. Okay, it is with respect to input volume. Okay, so that is receptive field. There is another question. Okay, this kernel size. Okay, so kernel size should be small because it is connected to the it is the weights. The size represent the weights that we have to use. Okay, so the number of weights have to be kept lower with a lower kernel size. Okay, and yeah, this is another question. Okay, this is the size of the uh, size of the what do you call this uh, size of the feature map. Okay, that will be produced. So and this is the initial feature map we have. After 32 filters, the this depth is divided determined by the number of filters. It will 32, right? And you can use this formula. W is the 663 here. Okay, F is minus 7. Okay, so minus 7 plus P is 0 divided by 2 plus 1. This is the answer. Okay. uh, Next,
Sir, please go to the previous slide, sir.
okay,
What is the answer? I could not got it, sir. Which one, sir?
C is the answer. Okay, so it with first 32. Okay, the depth will be 32. Next, what we have here is this W is the size of the image, that is 63, right? And filter size is 7, so 7. P is no padding, so 0 divided by stride is 2 and plus 1. Okay, how much is 56 by 2? 28 plus 1 is 29. The size of the image is 29 cross 29. Okay, and the 32 is the depth. Okay, got it.
Okay, sir. Thank you. Thank you, sir.
Next, so vanishing gradient problem is not there, so that is asking, that is the problem. Okay, so so as you know, sigmoid, the derivative tends to 0 with every repetitive steps of backpropagation. Okay, but in leaky ReLU, the derivative, as you can see, the the gradient means that we have to draw something. Okay, so so as you can see, tends to 0 as this value increases. Okay, so at every iteration this increases. Okay, and but in ReLU what happens that this like this. Okay, so gradient never goes to or tends to 0. What I have marked leaky ReLU because in negative values it has a slight non-zero value. Okay, so so that is why leaky ReLU never goes to 0. The gradient never goes to 0. Okay, and this is from the paper VGG network. This 3 cross 3 kernel with stride 1 is used. Stride 1 because the size of the image is not reducing. 3 cross 3 kernel because it is written in the paper. Okay, so inception model we have seen that this is parallel convolution operation. Okay, so if you look at the paper and see the answer, actually nothing special here. So I explained the gradient clipping concept. So in some deeper networks, especially recurrent neural network, okay, which I don't think will be covered in this course. Okay, so in recurrent neural network RNN, what happens is that the gradient blows up. Okay, and you have to set a threshold, higher threshold, so that you can. So it is called gradient clipping. Okay, suppose the clip gradient is 1000, so it may blow up to infinity, but it will always be kept at 1000. Okay, so it does not blow up. Okay, so that is the concept of gradient clipping. And the stride with stride 2, whatever stride x, suppose, so the image size of the image will become 1 by x. Okay, 64 becomes 32 cross 32. So that's very simple as well. So this is from paper. How many convolution layers are there in Alexnet? That is 5. Okay, Alexnet very important paper. And the number of maximum number of training parameters, as I have told, because it has the highest number of fully connected layers. Okay, so that is why the parameters are highest in VGG 16. Okay, got it.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much.
Okay, very nice.